Hey everyone, and welcome to this explainer. I am super excited you're tuning in today because we're going to demystify something absolutely foundational to our modern world. We all talk about the cloud like it's some sort of invisible magic, right? But the reality? The digital world is built on cold, hard, physical foundations. Today, we're unlocking the very first layer of the internet, the OSI physical layer. So let's jump right in and see how all of our data literally travels across the globe. Real quick, here's our roadmap. We're going to start with a high-level look at the OSI model, then zoom right in to meet the physical layer itself. From there, we'll explore cables, light, and wireless tech, check out some Layer 1 network devices, map out physical topologies, and finally, wrap up with some real-world troubleshooting. All right, Section 1. To really understand the bottom of the internet, we kind of need to see the whole stack first. The OSI, or Open Systems Interconnection Model, is basically a 7-layer map that explains how our devices communicate. Imagine you're sending a simple hello on WhatsApp. That message doesn't just magically teleport to your friend. It starts way up at the top, layer 7, the application layer. And as it moves down the stack, it goes through this process called encapsulation. It gets chopped into little pieces, addressed, formatted, and checked for errors. By the time it hits layer 2, the data link layer, it gets a MAC address. And then finally, it hits rock bottom, layer 1, the physical layer, where it's transformed into raw signals that can actually leave your phone. But I've got to point out a pretty crucial technical distinction here. While we use this 7-layer OSI model as our super detailed educational map, the actual real-world internet runs on the TCP/IP model. And that one simplifies things down to just 4 layers. You can think of OSI as the theoretical blueprint that teaches us how it all connects, while TCP/IP is the practical, revved-up engine that's literally powering your web browser right now. Okay, moving on to Section 2. Let's officially meet the star of today's show, the physical layer. We are going right to the absolute bottom of the stack, where digital logic slams into physical reality. So, what exactly is it? Well, the physical layer is the first and lowest layer of the OSI model. Its one and only job is to take raw digital data and transmit it over a physical medium. Down here, there is absolutely no concept of IP addresses, MAC addresses, or smart routing. None of that. It deals exclusively with raw hardware. We're talking electrical voltages, pulses of light, or radio waves. To grasp this intuitively, just think of the physical layer as the road itself. The upper layers, those are the cars, the traffic lights, the GPS navigation. But layer 1 is just the asphalt. It genuinely doesn't care if the cars driving on it are carrying emails, massive video games, or 4K streaming movies. It never checks the cargo. It simply provides the physical path for all that data to travel on. The fundamental unit of data at this level is the bit, literally just a single 0 or a 1. That's the full shebang. Everything you do online gets broken down into these tiny units. The physical layer takes these zeros and ones and puts them through a process known as encoding. Encoding is basically the magic trick of translating a digital 1 into a quick spike in electrical voltage or maybe a flash of light, so it can physically cross a real distance. And to push those bits out into the real world, Layer 1 relies heavily on 3 main types of signals. First, we have electrical signals, which zip through copper cables. Next up are optical signals, which are literally pulses of light shooting through glass fibers. And finally, radio waves, which beam data through the air without needing any physical wires whatsoever. Which perfectly sets us up for Section 3. Let's get a little closer and look at the specific media that make up these digital roads. When we talk about copper wiring, you're mostly looking at twisted pair cables. You probably know this as a standard Ethernet cable. You've got UTP, or unshielded twisted pair, like your typical Cat5e cable, giving you about 1 gigabit per second. It's cheap and it's everywhere. But then you have STP, shielded twisted pair, like a Cat6 cable. These are built for much higher speeds, up to 10 gigs, and they're shielded against EMI, which is electromagnetic interference. And here is a super cool technical detail. Ever wonder why the internal wires are twisted? Twisting those copper pairs physically cancels out that electromagnetic interference and prevents something called crosstalk, which is when signals bleed over from one wire to another. Now, before we start bragging about internet speeds, we need to clear up 3 concepts that get mixed up all the time: bandwidth, throughput, and latency. Bandwidth is purely theoretical. It's the absolute maximum potential capacity of a medium. Think of it like the physical width of a water pipe. Throughput, on the other hand, is the actual, real-world data transfer speed you're getting at any given second. You might have a cable with a 10 gigabit bandwidth, but thanks to network congestion, your throughput is way lower. And then there's latency. Latency has nothing to do with capacity, it's all about delay. It's the literal fraction of a second it takes for a single bit to travel from point A to point B. Moving away from copper, we hit the big leagues, fiber optics. This is the ultra-high-speed backbone of the internet. Instead of electricity, fiber uses light. This gives it two massive, game-changing advantages: mind-blowing speeds and total immunity to electrical noise. We generally see two types here. Single mode uses a single direct path of laser light for insanely long distances. Think connecting entirely different cities. Then there's multi-mode, which bounces multiple light paths for shorter runs, like inside a corporate data center. Fiber also rocks because it has extremely low attenuation, which is just a fancy way of saying the signal doesn't fade out easily over long distances. But hey, Layer 1 isn't strictly about stuff you physically plug into a wall. We also have unguided media, aka wireless communication. Technologies like Wi-Fi, running on the 802.11 standard, your Bluetooth headphones, or the 4G and 5G networks on your phone, they all operate right here at the physical layer. They're just encoding those digital bits into radio waves and broadcasting them invisibly through the air. So, the huge takeaway here is that whether it's copper, glass, or literal air, it is all Layer 1. Let's move into Section 4 and check out the actual hardware devices that live exclusively on this bottom layer. First up, we have the repeater. Remember that word attenuation I mentioned a second ago? The natural fading of a signal over distance? Well, a repeater is a simple Layer 1 device built specifically to fix that. It grabs a weak, degraded incoming signal, cleans it up, regenerates it back to its original full strength, and shoves it further down the line. Next, we've got to talk about network hubs. But I actually want to throw a question your way first. In modern networking, hubs are basically dinosaurs. They are practically obsolete. Why do you think network hubs are considered so horribly inefficient? Take a second and think about what a device strictly locked to Layer 1 actually does. The answer completely comes down to how dumb they are. A hub operates solely at the bit level. It's essentially just a multi-port repeater. If a signal comes into port 1, the hub blindly yells that exact same signal out of every single other port it has. It doesn't look for MAC addresses, it has zero smart routing. Because it just blasts everything to everyone, it creates massive data collisions on the network. It's incredibly inefficient compared to a modern switch, which operates intelligently up at Layer 2. Another classic Layer 1 device is the modem, which is short for modulator-demodulator. Your computer naturally speaks in digital, discrete signals. But older telephone lines, like the ones we used for DSL internet, were built entirely for continuous analog waveforms. A modem's sole job is to translate between those two worlds. It converts your digital bits into analog waves to travel the wire, and then translates incoming analog waves right back into digital bits on the other end. Okay, so now that we've got the cables and the devices down, let's hit Section 5, Physical Network Topologies. This is all about how we actually arrange this hardware to build a functioning network. There are a handful of main ways to map out a network. The bus topology uses one single main cable that everything taps into. It's simple, but if that central line snaps, the entire network is dead. The ring topology connects devices in a closed loop. A mesh setup connects almost every device directly to every other device, giving you absolutely incredible redundancy. But the undisputed king of local networks today is the star topology. This uses a central device, usually a switch, with individual cables radiating out to each computer, like a star. The massive advantage here: if one cable breaks, only that specific computer goes dark. The rest of the network keeps humming along perfectly. Which leads us perfectly into our final section, troubleshooting Layer 1. How do network engineers actually use this OSI theory in the real world to fix broken stuff? Listen, when the internet breaks, a good engineer never instantly starts messing with DNS settings. They use a structured, bottom-up approach based directly on the OSI model. Step 1 is always the physical layer. Is the cable actually plugged in securely? Is the link light even blinking on the network card? Did a mouse chew through the wire? Only after completely confirming Layer 1 is healthy do they move up to Layer 2 to check the switch and MAC addresses, and then to Layer 3 to verify the IP address. Sticking to this structured approach literally saves hours of hair-pulling frustration. As we wrap up this explainer, I want to leave you with one final, slightly mind-bending thought. If the physical layer just magically disappeared tomorrow, the entire digital world would instantly freeze. No bits, no routing, no internet. Period. So take a look around you right now. Are you sitting on Wi-Fi? Are you hardwired into an Ethernet port? What physical connections are silently powering your digital life at this exact moment? We love to use the cloud as a metaphor, but at the end of the day, it's all just cables, light, and radio waves. Thanks so much for joining me to explore the foundation of it all. Keep learning, stay curious, and I'll catch you on the next one.